Pre-ACT 2020-2021, Passage 3. Passage 3 is a data representation passage. And we can tell that because there's very little reading. And it doesn't say experiment 1, experiment 2. All right, so once again, we're going to jump right to the questions. Let's look at our figure. There's figure 1 here. Jupiter, Io, Ganymede, blah, blah, blah. View from Earth, west to east. Okay, view from above. All right, and then I have a graph, and I have these same terms over here. And if you don't have to know this, but this is talking about Jupiter's moons. These are Jupiter's moons. All right, so it looks like I've got arc seconds here. What the heck is an arc second? An arc second is the farther from Jupiter moon appears to be, the greater its angular separation. That's what theta is. So that's theta. Figure 1 shows these moons positions midnight. Okay, so if I look at the bottom, my x-axis, the x-axis goes from June 20th to June 28th, so it's 8 days, and these little marks on the graph between the dates are times, because it goes from noon on one, it goes from noon, so those are time. It's talking about noon there. All right, so let's jump to the questions. Question 13. The number of orbits per week is a measure of orbital frequency based on figure 2. Okay, so when I look at figure 2, that's my locator. Figure 2 is my locator. Frequency is these waves. Frequency and wavelength. So I'm looking at these waves, and that's the frequency with which a moon orbits Jupiter. Okay, so which Galilean moon has the highest orbital frequency? So which line on the graph has the highest number of peaks and valleys? So that would be this one, which is Io. So that's that. 14. Based on figure 2, Callisto, so I'm looking at figure 2 again, Callisto completes one orbit around Jupiter in approximately how many days? All right, so Callisto, it's this dash dot, so it's this line. Well, it doesn't even make one complete revolution. One wave would be like this, from trough to trough, or peak to peak. This is not even half of a wave. So then that means it's got to be longer than 8 days, which is why it's J. All right. 15. Based on figure 2, as viewed from Earth at midnight on June 27th, which Galilean moon appeared farthest west of Jupiter? Okay, so let me see. So noon is here. So at midnight it would be here. And I'm looking for which Galilean moon is farthest west of Jupiter. Okay, so west. If I look over here, I'm going to look at this graph, this figure 2, because west. So if I look east, it looks like Io, Europa, and Callisto are east. West is Ganymede. Okay, let's look at this. Ganymede is the dotted line. Well, on the 27th, the dotted line is the one that is furthest west. So if I look here, west. All right, had to use both. Well played, ACT. So we're going with Ganymede. 16. Based on figure 2, at noon on June 23rd, theta for Ganymede was approximately. June 23rd, noon is right here. Okay, so I've drawn this pink line, and I'm looking for Ganymede, the dotted line. So I'm going to go up here at noon until I hit the Ganymede's line, and that is right on 10 east. So 10 arcseconds east. 10 arcseconds west, it definitely wouldn't be that. 14, no, it's not. 14 would be way up here, so that's not it. And that one's west also. All right, based on figure 2, my locator, at which of the following times in 2012 was the angular separation for Callisto closest to 20 arcseconds east? Okay, now, I need to look at my choices for this one, because if I look at it, I notice it's either June 26th or June 27th. So I don't need to pay attention to any of the other dates. So I'm looking for Callisto closest to 20 arcseconds east. 20 arcseconds east, Callisto. Let's see, and I'm looking over here at the 26th or the 27th. 26th or the 27th. Keeps going over here, over here, over here. So it looks like it doesn't hit the line. 20 arcseconds east doesn't hit the line until late on the 27th. So that would be, so 6 p.m. on the 27th, so I can cross off the 26th. Let's do that. 6 a.m. Nope, we decided it's late in the day, so it is 6 p.m. So there's another one of those modeling questions. And first of all, I figured out I could disregard the 26th because it went past the 26th, and my line I was looking for was on the 27th. So then I just had to figure out whether it was 6 a.m. or 6 p.m. All right, the last question. Oops, here I am pointing at it, and I'm not even showing it to you. Okay, so once again, I could cross off the 26th, and then I just had to figure out whether it was 6 a.m. or 6 p.m., and we decided that it was 6 p.m. It was late in the day. All right, Thebe. Thebe is one of Jupiter's smaller moons. Thebe completes one orbit of Jupiter in approximately 0.7 days. Based on figure 2, so I'm going to look at the graph, regardless of direction, the maximum value of theta for Thebe is most likely, okay, so I'm looking less than 7, between 7 and 10, between 10 and 13, and above 13. All right, so if I look at my graph, now when I look at this 0.7 days, if I just look here, it would be roughly this far to complete one complete revolution. Okay, now the theta that is closest to that many days would be Io, and Io is 5 arcseconds. Okay, see that? Theta is 5 arcseconds. Notice that when the wavelength increases, the arcseconds increase for each of them. So if I'm going to go the other way, if I'm going to decrease my frequency, the arcseconds would decrease. So it has to be less than 5 because the smallest frequency has an arc second of 5. So if I'm going to go with an even smaller frequency than Io, it needs to be less than 5 arc seconds. So let's look at my choices again. Less than 7, between 7 and 10, nope, and then these are all above 10, so my answer is 7. Okay, and most of these were interpretation of data or scientific investigation questions where you had to do what we just did and interpolate or extrapolate a line. All right, passage 3.